Okay, in this video I wanted to finish up section 2.3. We're looking at calculating limits using the limit laws. And I had gone over the limit laws here on this other sheet. And then we've already looked through, gone through several examples here of evaluating limits using our limit laws. And a lot of the problems are going to be where you're going to have to algebraically manipulate the inside. Okay, because you can't make a direct substitution. So let's do some more problems like that. Here's another example. Okay, now notice that I can't directly substitute 0 into the function because the square root of 9 is 3. 3 minus 3 would give me 0 down under, and I know I can't divide by 0. Okay, so there's going to be some work to do here. I need to algebraically manipulate the inside and trying to make it so that I can directly substitute that number in. Now, the last problem that we saw, which was in the last video, involved a radical inside the limit, and I was rationalizing the numerator. Okay, I'm going to do that here, although I'm going to rationalize the denominator, and let's see what that does. So rationalize the denominator just means make the denominator no longer contain a radical. To do that, you'd multiply the top and the bottom by the conjugate of the denominator. The conjugate of the square root of 9 plus 7t minus 3 would be the square root of 9 plus 7t plus 3. Okay, so I'm going to multiply the top and the bottom by the square root of 9 plus 7t plus 3. And there's no harm in doing what I'm doing here, right? This is just 1. So I'm not actually changing the inside. I'm changing the form, but I'm not changing what the resulting numbers would be, right? If I'm just multiplying by 1. Okay, now in the numerator, I'll just leave that as is, I guess. And then in the denominator, I'm going to FOIL that out. Square root of 9 plus 7t times the square root of 9 plus 7t, that would be 9 plus 7t. Now the reason for using the conjugate is because the middle term is going to go to 0. So we're no longer going to contain a radical in the denominator, and that's what I want. Okay, so go to the last term here. Negative 3 times 3 is minus 9. 9 minus 9, those can cancel. After you've canceled the 9s, you can then cancel. Here's t, can cancel with this t. And so that leaves me with the limit as t approaches 0 of the square root of 9 plus 7t plus 3 all over 7. Okay, well, now there's no problem with directly substituting in 0, right? I've got 7 in the denominator. I'm not going to get 0 there. So that's what I've done. Remove the limit notation. And we've got the square root of 9 is 3, plus 3 is 6. 6 over 7 then would be my answer. Okay. I mentioned the importance of using good notation in the last video. I want to re-emphasize that here. When you're calculating limits, make sure that your notation looks good. Make sure that you're writing the limit notation down. Make sure that you're writing the function inside the limit. Make sure that you're removing the limit notation after you've calculated the limit. Okay. Make sure that you're simplifying. Make sure that the answers are in exact form. Okay. These are all things that I will be grading you on in the assignments. And this is how the book is going to want it also. Okay, so it's not like we're doing something different from what the book is wanting. And by the way, whenever you have a limit calculation that involves a radical, one of the first things that you'll want to think of if you can't directly substitute in the number is to rationalize either the numerator or the denominator, wherever the radical happens to be. Okay, that in general is like one of the things that we'd want to think of early on. Okay. Here's another example. Let's find the limit as x approaches 2 of 1 over x minus 2 minus 4 over x squared minus 4. Okay. Now, if I were to split this into two limits, that wouldn't be wrong, but it wouldn't help me because I wouldn't be able to directly substitute in 2 into either one of those two limits. So at that point, I would be stuck. So I wouldn't want to look at the problem by doing that. Okay. But rather, let's algebraically manipulate the inside, okay? I want to get a common denominator, that way I can add these two fractions together. So on the first term, let's multiply the top and bottom by x plus 2, x minus 2 times x plus 2 is x squared minus 4, and that gives me my common denominator that I need. So I can keep the denominator and add the numerators. X plus 2 minus 4 is x minus 2. I'm dividing by x squared minus 4, which is going to factor as x plus 2 times x minus 2. X minus 2 can cancel, and that'll leave me with 1 over x plus 2. The limit as x approaches 2 of 1 over x plus 2, well, there's no harm with plugging in 2 now, right? I'm not going to get 0 in the denominator. 1/4 would be the answer on that one. A lot of what we're doing here, I feel, is just, using some algebra. You're manipulating the inside. It's a lot of simplifying, okay, and canceling and things like that. Here's another example, and then we'll talk about the squeeze theorem. So suppose that we want to find the limit as x approaches 5 from the left of x squared minus 3x minus 10 over the absolute value of x minus 5. Now this is a one-sided limit, right? I'm approaching from the left, and we talked about one-sided limits in the last section. Okay, well, there's still a problem with direct substitution, right? I can't directly substitute in 5 because I know I can't divide in by 0. However, I want to look at how we define the absolute value of x minus 5. The absolute value of x minus 5 is x minus 5 if x minus 5 is greater than or equal to 0, or x would be greater than or equal to 5, right? And then I want the opposite of x minus 5 if x minus 5 is less than 0, or x would be less than 5. Okay, now all I'm saying here is a way to describe to somebody that anything coming out of the absolute value bars is never going to be a negative. Okay, I've got a piecewise definition. So, let's suppose that x were 3. Okay, well, 3 minus 5 is negative 2. The absolute value of negative 2 is positive 2. Now, that's what I'm saying here in piece 2, right? X is less than 5, so if I've selected 3, I'm supposed to use piece 2 when I plug in that number. 3 minus 5 is negative 2, but then I want the opposite of that number. So piece 2 is really saying, hey, if you get a negative inside of the absolute value bar, take the opposite of that number. That way you have a positive coming out of the calculation. Otherwise, if x is greater than or equal to 5, you're not going to have a negative inside, so just use that number that you've already got there. Okay, anything coming out of the absolute value bars is never going to be a negative, is essentially what we're saying on that. Now, this piecewise definition is useful to us because I'm approaching 5 from the left. So if I'm approaching 5 from the left, x is less than 5, which means that I want to be using piece 2 here. And so the absolute value of x minus 5 would be negative the quantity x minus 5. I can lose the absolute value notation since I know I'm on the left side of 5. Now, I still can't directly plug in 5, but the numerator is going to factor and allow me to cancel x minus 5 with x minus 5 there. The negative can come out of the limit calculation if you want, or not. You can keep it inside too, that's fine. But now you can directly substitute in 5. The fact that we're approaching from the left is not relevant anymore. Because I can directly substitute in the number, I'm going to go ahead and do that. Remove the limit notation. 5 plus 2 is 7. Negative 7 would be my answer. Okay, now of course in this problem, the key thing is to use this piecewise definition. Okay, if I didn't do that, if I just remove the absolute value bars, I'm going to get a wrong answer. I'm going to get 7 then as the answer, which is wrong. Okay, so knowing this piecewise definition would be important. Now, if I were approaching 5 from the right, then I'd be using piece 1, and I would just simply remove the absolute value notation, and I'd get 7. Okay, but again, I'm should be considering this piecewise definition though in the calculation. There's a couple of problems in the book where you've got absolute value expressions. So consider that what you see here as an example when you are working through that. Okay, the last thing that I want to talk about then in this section is called the squeeze theorem. We sometimes call this the sandwich theorem. Okay, it's the same, means the same thing. And here's what the squeeze theorem says. If you have 3 functions, f, g, and h, And I want it to be so that f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except for possibly at a. In other words, this inequality doesn't have to be true at x equal a, okay, but anywhere around a, I want it to be so that f is less than g and g is less than h, okay? Then if the limit as x approaches a of f of x is the same as the limit as x approaches a of h of x, and I'll just call that L, okay, like those two limits exist, then the limit as x approaches a of the guy in the middle, g of x, is also going to be that same number, okay? In other words, so g of x is squeezed between these other two functions, okay? If f and h have the same limit, g is forced to also have the same limit, okay? The squeeze theorem can be handy in some calculations, and sometimes it's our only option in calculating a limit. So let's take a look at an example here. In this one, I want us to show that the limit as x approaches 0 of x squared times sine of 1 over x is 0, okay? Now, by the way, I'm multiplying, but my limit law, the limit of a product is the product of the limits, is not something that I would want to consider here, because the limit as x approaches 0 of sine of 1 over x, so we have already looked at that problem before. That was in the last section, and we saw that that limit does not exist, right? That's the one where you're oscillating between 1 and negative 1. You're not approaching any one particular y value if you're just bouncing between 1 and negative 1. Okay, so that's a problem. I don't want to be using just splitting this into two limits if one of them doesn't exist, right? Now, the goal in using the squeeze theorem is to try to find functions f and h that you do know the limits of. Okay, so I do know that values of the sine function are always going to be between negative 1 and 1. Right? Sine of an angle is always going to be between 1 and negative 1. It doesn't matter what that angle is. Now here the angle is 1 over x. That's okay. I'm always going to get a y value that is between 1 and negative 1. Well, if I take this inequality now and I multiply throughout the three parts by x squared, then I've got negative x squared less than or equal to x squared times sine of 1 over x less than or equal to x squared. Now, I'd like to know the limit of the guy in the middle, right? That was the original question here. And I know that the limit as x approaches 0 of negative x squared is 0, right? I can just directly substitute in 0 there. There's no problem with that. Also, the limit as x approaches 0 of x squared is 0, right? These are very easy limits to calculate. I just plug in 0, okay? Now, this function is squeezed between the other two. Therefore, by the squeeze theorem, the limit as x approaches 0 of the guy in the middle here, x squared times sine of 1 over x is also going to be 0. Okay? Now, and by the way, the squeeze theorem in this problem is my only option. There is no other way to show the value of this limit as 0 other than to know the squeeze theorem. And that'll sometimes happen where you're going to have to use, something that's your only option. Okay? If we could look at a graph of this, I've actually drawn the graph here, but using my calculator, I can just quick show you where that came from. So if I go to y equals, I've already got this typed in. I'm using this inequality here that I've formed. Okay, so y1 is going to be negative x squared, y2 is going to be x squared, and y3 would be x squared times sine of 1 over x. Make sure that you're in radian mode also, otherwise the graph will not look anything like what you see here. Okay, sketch the graph, and yeah, so that's what I had drawn there. Okay, what I saw from the calculator, and you can see that we have x squared times sine of 1 over x is squeezed between these two parabolas. So if the limit as x approaches 0 of x squared is 0, and the limit as x approaches 0 of negative x squared is 0, well, this function squeezed between the other two means that the limit as x approaches 0 of x squared times sine of 1 over x is also going to be 0. By the way, I've indicated the window that I was using there. I can just show you real quick. I had set that up there also on the screen. And the values that I was using here weren't for any particular reason other than I just thought that, it was a good viewing rectangle so that we could see all three graphs there. Okay, at this point we're now done with section 2.3. So here's the homework on page 102. Be sure to look at the odd numbered problems that are listed there for me when you get a chance.